Hello from your favorite artist electronist, Mr. Q12. The last movie that I made is number 270, and it's called How to Make a Transistor BD681 Work at 12 watts. I'm very certain that I made a mistake there, but by not doing something. So my last experiment there, I didn't took some essential measurements. Suffice to say that I made a mistake, and by not measuring. I push this entire circuit and this transistor that is here under this clamp. I push it to the maximum, incremental like that, and I reach 8 volts at 5 amps. It is summing up to 40 watts. So I was in ecstasy. I was extremely happy that I reached this very high value, the maximum value of this transistor that it can run. But like I said a moment ago, I made a terrible mistake by not measuring inside the circuit here, which it means here. So this is my friend name, DL324 from AAC forums. And this guy, he is definitely an American from Pacific Northwest, and is from Portland or Seattle, because this Pacific Northwest, it doesn't tell me anything, at least to me, and is somewhere in the north of America, very close to Canada. It's in the border, actually, very close to the border with Canada. And he is from that location because he didn't put a name, and I had to use Google Maps to actually find out where that area, that Northwest Pacific is situated. I'm diametral opposite on the other side of the globe from his position, so I have no idea how things are named in those areas. This American friend of mine, who was very helpful, he actually mentioned that this is his circuit diagram actually, and he helped me along the way, along the road, while I was building it, while I was testing everything. Of course, I got in the woods with the testing. He didn't mention to get this extreme like I did here. He made his device very simplistic, but I tend to overcomplicate things because I wanted to test, and I wanted it to work actually for other things. But it became something else. Now this circuit, it transformed into a transistor tester instead of testing other components like a LM317 voltage regulator and such, because that was the original intention for this circuit. So this, because I cannot drive at higher power and higher current, this circuit transformed itself into a transistor tester for this power transistor that I'm testing here, this BD681. And that's a little bit of unnecessary history. So my friend, my American friend, he told me to actually test in circuit some values. He didn't specify what to test. He only told me to start to think on testing things, because this is normal. And I believe him, of course. He's my friend, and from America. and the easiest test that you can do in anything, in any circuit that you have, is to take voltages. So this is the first step that I did. I started to collect voltages. I probably got more voltages than I needed initially when I started testing, but then I draw a line with the most important, and I keep on reading only these components values. There are 3 components. It's this transistor here, collector emitter voltage, this L6 voltage that is falling over it, and this base from this very small transistor here, or the output of this op-amp in the same time. So I'm shooting 2 rabbits with the same reading, but this to ground. I'm putting the probes here and here. So here, for the resistor, I'm measuring here and here, and for the transistor, I'm measuring collector and emitter. This is where I'm putting the probes of my multimeter. Here it is. Exactly with this one I'm measuring. I'm getting the voltages. So this is the easiest and convenient way to get some data from your circuit, getting voltages. All right. So this is clear, okay? All right. So all this that you see here until here, all this data here, you see is not valuable, is not correct anymore, because this value that I'm having here, that I was very ecstatic, that I was very happy when I've seen this 40 watts. But my friend DL324 from America, my American friend, he was not very happy, and he told me something is wrong. This values, this data that you collected from your circuit is not adding up to something in his head. He didn't explain to me what. But even he was mysterious like that, I believed him that is not correct what my readings were. So I started to think for myself, of course. So here it actually says that the 40 watts test. I actually made a very long discussion with my friend of what can be. Then I made myself a calculation, and I will show you right now. Okay, so I actually had to go back and look on my analysis that I did. Actually, this is my interpretation of how stuff should work. And I asked him, is this shit what I'm doing here correct, all this data? And he didn't comment on anything. He was commenting if it was something wrong. He was jumping and correct me right away. So assuming that he didn't told me explicitly yes or no, I believe this is correct. And what I did, these are the values from here. So remember, this is PSU. Let me actually write it here. Power supply unit data. This is the voltage and the amperage that my power supply was showing me. That power supply. It was written there on its display. Okay, so this is the data from the power supply, and this is collected data here. Collector emitter here and here. So Q3 is this value that I measured, 5.4 volts times 5 amps that my power supply was showing. So I'm assuming all this amperage is the same in the entire circuit. Theoretically, I didn't measure it. So this is another mistake. I didn't measure the actual current in the circuit anywhere. I only measured some voltages, and from these voltages I deduced and I imagined that this amperage is consistent. Theoretically it is, but who knows with this type of power circuits. I should have measured it, but let's walk on this path that I already made here. So this Q3, which is this transistor, this power transistor that I'm having here, is the measure. I took the measurements here on collector and emitter on these 2 points, and I got this 5.4 volts times 5 amps equal 27 watts. So now I'm getting the real, a bit, I am getting more closer to what the wattage dissipation was on this transistor. I originally believed my power supply value of 40 watts. I was thinking my transistor was getting those 40 watts by itself is so powerful. After this calculation, after this voltage reading and calculation, I get this 27 watts, which is almost half of what I'm having here. So I took the value from R6 as well. I read it over it from this point to this point here, and it's these 2 points actually, exactly these 2 pins, and it's 1.08 volts, almost 1 volt or 1.1 times 5 amps equal 5.4 watts dissipated on this power resistor. So voltage on collector emitter, and I'm talking about this power transistor here. I'm getting this voltage here plus voltage here. So voltage on collector emitter from Q3, this guy here, plus VR6 voltage on resistor 6 here, equal these 2 guys here, 5.4 plus 1.08, and equal 6.48. So my power supply unit is showing me that is delivering 8 volts. So 8 minus this value here, these 2 summed up, equal 1.52 volts dropped somewhere else in the circuit. I'm getting a voltage loss exactly where it was starting to happen very seriously on my breadboard until I move it aside and I made this other circuit that I'm having here, which is more resilient and is better, way better than the breadboard itself. On the breadboard I was getting even more serious than this voltage losses on the power tracks. Here, on this positive and this negative, exactly on the power tracks, I was getting the losses. At this point, I deduced, or I thought, because I encountered this problem in my life other times. So I made serious mistakes before, and I didn't realize some details. And these are details. What I'm having here is a very detailed problem, and these details are summing up to create a bigger problem. That's the problem. That's the real problem. The devil is in the details, pretty much. So these are the details. So I'm assuming it's the wires at this point. This 1.52, I was certain it must be the wires that I'm having in the circuit. And before, I will show a picture. I will show you how the wires were before. And this is now. Let me show you right now how this is how thick the wire is. You see, I changed the wires from my power supply unit. This is in comparison how thick they are. Looking like they are the same, but they're not. Trust me on that. This is a little bit smaller, and the diameter is, you see that it's a dinky in the middle, very, very shitty. Let me do it like this. You see, it's a very shitty, it's less than 1 millimeter what is having there. While this is having, you see how much plastic, how much plastic is having here. There's a ton of plastic here in the mid of the diameter of the, it's very thick plastic is having. But this is not having that much plastic, and it's having 2 millimeters conductor that is having inside. Compared with this 0.8 is less than 1 millimeter, because I use my calipers and I put on 1 millimeter and I was doing it like this. It was having a large tolerance. So that's definitely less than 1 millimeter. So these are the wires that I was having before I changed with this thicker one. And I also changed the alligator clips as well, because as you can see in comparison, because these alligator clips that I'm having here, they couldn't support this 2 millimeter wire that I'm having here, the diameter on them. It was too big, too inconvenient. It was big, too way stupid big, and I had to use a bit more larger alligators. I have even larger than this, but these were like intermediary. Okay, that's it about that. Let me finish my analysis that I'm having here. So assuming is the wires, their resistance must be R equal V over I equal 1.52, which is this value here, over 5 amps, and equals 0.3 ohms, a third of 1 ohm. And they get 1.52, so this value here, times 5 amps equals 7.6 watts dissipated only on the wires themselves. And when I was discussing about these things, I had the idea to, the next step was to check the wires if they are getting hot. So I literally did this. I put my hand here and I keep it like this. Of course on this other wire, because this was the wire that was before, and I was keeping it, and it was getting warm. It was not hot, but warm. So I was right. It was some power losses on the wires themselves. And here, all these 3 wires that you are seeing here were this thickness that you are seeing here, very, very thin wire that were going to the power transistor. And I put my finger on them, but I couldn't grab them like this. I only pressed them on the table. I wasn't very certain if they were hot or cold. I couldn't tell. So I took another reading. I changed the cable, this main power cable here. I changed it, and I took another reading from the PSU. This is the value from the PSU, and I took one single reading of the collector emitter. But then I said, well, this wire should be changed at this point. I only changed the power wires that I'm having here, but these were remaining the same. I took that reading and then I stopped and I said, yeah, I really have to change these wires. So you are seeing here two types of wires. There are three wires, but two types. This thicker wire type and this very thin wire type. But why I didn't put this thicker wire everywhere? Well, because first of all, I only had this length of wire. It was not cut, so I had to cut it to make two wires out of it. It was one single long wire, and I didn't want to cut it, but after all, I did cut it. This lengthy as it is, as you can see it here. But then I was on the point of cutting another very thick wire. This ground wire that remained from this cable that I collected, these two wires, which is having 2 millimeters. And then I realized that this is a base, and this wire is this wire here. Is going to the base of this transistor, of this power transistor. So it doesn't really need a powerful wire to conduct too much amperage on it. It's a very low amperage and very low voltage also as well on this particular link or wire that I'm having here. So that's why I leave it as thin as it is, as you see it right now. And I only put this very powerful or very, very strong, very thick wires only here on the collector that is going to the positive. And this wire from here to here, which is the emitter of this transistor, to this point, where it's getting into this resistor and going to the negative ground point here. So that's this is the logic why I use two thick wires and I leave this very thin wire here, because it's having sense it doesn't have sense to have a very thick wire on the base of the transistor. That's it. So now there are two wires, and I measure the diameter of the wire that is inside this plastic hose, and it's exactly 1 millimeter. So right now I'm having also 2 millimeters of conductor wire from here to here, and also from there to there. I also changed the resistors. Before I was having 0.23 ohms made from two resistors, and another one of 0.3, one single resistor power at 3 watts. But this, what I'm having here, is 1 ohm at 10 watts per one resistor, and I have 5 of them, all the same. So in parallel, as you can see underneath them, how they are linked there. And the power is exactly 0.2 at 50 watts, because all this wattage is summing up or close to 50 watts. Maybe it's not exactly fixed 50, it's probably 45 or something, because there is some tolerances in this resistors, 5% or 10% even. And all this thing that I'm having here, it represents 0.2 ohms or 200 milliohms at 50 watts, theoretically, what I'm having here. Because the other resistors that I had, when I was making this experiment for the 40 watts, those smaller 3 watts resistors that I put in parallel, summing up somewhere at 6 watts probably, 6 or 5, they were getting extremely hot, and I had to change them with something. And quite coincidentally, these resistors I get them from, I have them from 1 week from now. So this is the date. 02 is the day, 03 is the month, and 2024 is the year. I received these resistors, and now I already only 5 I bought. Only these 5, and I use them fully all, like they were prepared for this experiment almost. It is a very interesting coincidence that I'm having here with this particular resistors. This is 1.5, I believe, or 1.2 full core inside, and it's not stranded wire. This two blue. This is stranded wire. It's very malleable. You can move it very quickly. But this they stay stiff like that, as you can see. And I couldn't find thicker enough. Actually, let me show you the cable that I got. These wires that I got from. This is the, as you can see, as I told you, this is quite thin here. The plastic is quite thin, and the middle of the conductor, I cut it from this other side. From here I cut it. And probably this is better to show like this, probably, I don't know. And I measure with my calipers. I put my calipers there and I measure it, and it's exactly 2 millimeter of only the conductor, not the isolator. So I don't care about this isolator. I only care about conductor that I'm having here. So this was perfect. But as you can see, I have a remnant of a cable. This is the cable that I used in my entire room. You can see it actually here on my mains plug here and all over my room. So this cable, as you can see, is having 3 wires, not 2 but 3. So these 2 are the power wires here, and this third one is the earth wire. Is going directly into the earth, somewhere in the subsoil of my building. And this third wire, I have it here, and I didn't use it at all. I just scrapped it from this good cable, and I only used these 2 wires that were inside. You see, these 2 wires. That's it. That's the history of the cable. So on the internet, I'm getting these values of millimeter square area. It's an area which is very different from the diameter of the conductor that I'm measuring here. It's either 8 amps or 10 amps, this diameter. So this 5 amps should pass through all these wires that I'm having here quite freely without having any kind of resistance issues like it was before with this thinner wires. Okay, so I did this experimentation and all this thinking about, and I changed the wires and I made again the experiment. And this time I wasn't expecting, I was thinking maybe it's the same thing as before. I don't think it's, in some percent I wasn't sure if it's really the wires on these ones. So although I changed everything exactly as you can see here, I made a terrible mistake and I leave my power supply on the last setting that it was, all the knobs to the maximum almost. And when I powered it on, it didn't do anything for 5, maybe 10 seconds. So I was looking here, and for a few seconds, everything was like you are seeing it here. But in a fraction of a second, I could hear a hiss, probably a slight, very slight noise, and a white smoke from here. A very quick white smoke, like, and I believe it was even a spark, like a light flash, like a very quick light flash, like, and this is the soldier that is dead. Let me actually zoom in it, because this was an excessive power surge through it, and like here it was pressed very firmly, and it still managed to make a dimple there. Probably if it was not pressed, it was a larger dimple. You see, from a side is nothing, but from here you can clearly see it's something got wrong. Actually, I can test it right now. So what I'm having here is base. So now nothing is in power. That's why I can work freely like this. If it was in power, I was a bit afraid, so don't worry about it. So from here to here, nothing. From here to here, nothing. So yeah, it's completely dead, unfortunately. So I'm measuring from base to collector, positive, this positive on the base here, and this negative to the collector and to the emitter. So this is what I'm doing here, and I'm not getting anything. Yeah, it's definitely is dead. Rest in peace, my brave soldier. I will scrap your legs and I will use them somewhere else. And also this pad here with its leg, this middle leg is connected to that pad, so that's how I will scrap you. So it is also smelling as burnt as well. So next step was to dial everything down. All my potentiometers, all those potentiometers, actually these two mains, because these are a fine potentiometer and this is coarse potentiometers, and I had to dial everything down and make the experiment again from scratch, pretty much. And of course I changed the transistor with a new one that was staying somewhere here from my previous from my preview movie that I made when I tested that on the breadboard, that transistor. So I reached this stage here. So this is voltage here column, amperage column, and wattage column, exactly like before. And I took incremental measuring steps. I was also checking the temperature with my fingers, not with my thermometer, my digital thermometer, which is always here, by the way. And here I didn't note anything I should have for 5 and 12 watts, but I reached this stage at 7. I actually pushed it a little bit too high here, and it was getting quite hot. This entire element was getting quite hot when I'm measuring. I'm putting my 2 fingers here, and with this other 2 here, you see, on the sides, and I'm feeling it in different points. I'm feeling it like that, you see, and I can tell if here is more hotter than here, like this, doing, and the same here and here. At this value here, at 7 volts with 2.77 amps, I got 19 watts at 55 degrees Celsius. Then I took my digital thermometer and I started to get the temperature because it was way too hot for my fingers. And then I started to take the values to make the readings as I should do it before, in the very beginning, when I was very happy about the 40 watts thing. On my other experiment with my 12 watts that I made a movie about it, power and voltage losses in the wiring in the circuit, we can compare. Here is a bigger voltage than this. Here. Well, it's not a good comparison because there are different voltages. These voltages doesn't tell me anything at this point, but I made another secondary list like this. Here it is, the second reading. So this is in accordance with what I'm having here at this point. This is the last reading that I did here, and it's over that 50 degrees Celsius limit that I was imposing. In every experiment that I did, I was keeping an eye to be less than 50, but here I push it a little bit too high for this voltage to be a 7 here, most probably, and not to be a 6.87 or something weird number, you know, like here 2.77. This is the data that I get. I'll make a quicker analysis of this. So Q3, the transistor Q3, which is this, is getting the voltage from these 2 points here, and it's 6.02 volts times this amperage that I'm having here. So let me actually put it here, 7 volts, and this is 19 watts, and this is for the entire circuit wattage, not for the transistor, like I mistakenly believed before. So on Q3 is this voltage that I collected from these 2 points here, times 2.77 amps from my PSU. So this is power supply unit data here. It equals 16.6 watts over this transistor that I'm having here. This is the real, or very close to the real wattage that is passing through here. L6, which is this, or this here, is 0.67. Again, I took the reading between these 2 points, or there and there actually, 0.67 volts. times 2.77 amps equal 1.57 watts over this resistor. Voltage transistor plus voltage resistor equal these two values, 6.2 plus 0.57 equal 6.59. My power supply unit is delivering 7 volts here. So that's 7 minus these two elements here combined equal 0.41 volts dropped somewhere else. So here it was, you see, here it was 1.52 volts dropped somewhere else, and here it is 0.41, which is 3 times less than this, which is way more better here. But also the amperage and the voltage is way less than there. So again, probably it's wires, but this time I don't think it's the wires. This time I believe it's these metallic pads. They are not copper, a mild steel. It's a metal sheet that I bend it into shape to make these pads, plus the solder that I'm using there. It is putting some resistance, and probably that's where all this voltage is and the power is falling onto. Most probably, if I'm resolving these pads, I was thinking to make them from copper somehow, and to make the transition extremely clean transition, not impeded by some weird resistance in the tracks of the circuit that I'm having there. So if it's the wires, in this case, I'm assuming again it's some kind of wire somewhere, but also tracks, the pads, resistance, their resistance is V over I and equals 0.41, which is this value that I calculated here, that is dropped somewhere, over this amperage, total amperage of the circuit, equals 0.14 ohms. So this is 140 milliohms here, what I'm having. So and compare with what I'm having here, what I had here, it was 0.3 or 0.30. So this is half of that. Again, this is not very concludent because this is less voltage and less amperage, half of that wattage that I had there. So this kind of reflects that. I don't know. And they get 0.41 times 2.77 amps equal 1.13 watts dissipated on these pads. Probably were some wires that are weird. I cannot find them. And compare with 7.6, this 1.3 is okay-ish. But remember, this is little small elements, wires, little pads, all summed up is giving me this value that I'm having here. Is not one value for one element, is for multiple elements that combined, they are summing up to this value. That's the math that I'm doing here. And also that there, I wasn't getting that wattage on one single element, but on multiple, and combined, they summed up to that value there. So this is the video that I wanted, the update that I wanted to do. Unfortunately, I'm not showing anything that is working. Suffice it to say that I changed the wires. This is the conclusion, that this experiment that I did here helped me to think about a little bit more about power. When you work with power, you have to keep an eye on your wires, on your pads, these pads, tracks on the circuit. In my example that I'm having here, I'm using pads. Like I said already, it's a metal sheet that I'm bending, I'm cutting it and I'm bending and I'm forming it. It's a pad. But in your case, might be some tracks. If it's copper, then it's not such a big problem like I'm having here. But here is a bit more problematic because these are not copper at all. And they might put some resistance in the circuit. I know my stuff, I know my stuff, and I know with what I'm working here. So that's a problem. That's a big problem when I'm working with the high power. Unfortunately, this is in a sense, this is a disaster and a failed experiment and circuit, but it's also educative at the same time for some of you probably. My intention was to get the real power that I can drive this transistor here, how much power I can get it to work at. I forget to mention, when this transistor burned, I noticed and I actually smelled the heated metal from this radiator here because it is containing dust. It is very old and very dusty. Although I keep it in a box, it still collected some dust on it, or it remained from when it was in use. All this dust is creating a smell when this is heating up, and it's a specific metallic smell. And after I made the short, after I closed everything, I closed the power, and I was trembling a little bit because, it's not fun. It's not nice to have transistors blown up. I put very quickly, I took the measurements with my hands. I actually did it like this to see how hot it was, and it was extremely hot. So this is telling me that in a couple of seconds, 2, 3, maximum 5 seconds, because it was quite quickly. In 5 seconds, it got most probably over 100 degrees, or probably 150 degrees in 5 seconds until it burned out. So that much heat. It was an insane heat that it put this transistor, and this aluminum heatsink, it couldn't have time to dissipate very quickly that heat, and it accumulated here, probably in the center here, and it was very hot here on the margins as well, because this is a very well designed heatsink, and the heat is dissipating very quickly into this wings that is having here, that you can see on them, and that's very interesting phenomenon that I observed, and I forgot to mention it. So this is it about this failed experiment. Unfortunately, it's not completely failed because it is still working at a lower wattage than what I wanted it to be. You know, it's at 19 watts. It's half of this, what I'm having there. This is telling me that I should have even a bigger, way bigger, not 2 times, probably 4 times the area of this cooling heatsink that I'm having here. So 4 times like that. And this little transistor, probably like this paper that I'm having here, this big, and I'm not joking, and this little shit to stay right in the fucking middle of it, and and all the heat that is generating to be dispersed here so as quickly as possible, because the material is dissipating very quickly, the heat. And or probably a copper plate, a thick copper plate is much better than aluminum, but I don't have that kind of money, unfortunately, so I will have to find a solution somehow. I don't know how. Actually, my 2 friends, they showed me some they were bragging with their heat sinks that they have, and one of my UK friend from England, he showed me long radiator from AliExpress, and it was quite thick, and it was very large, like that probably, and that is actually perfect for my experiment that I'm having here. And that's a good, he bought it a couple of years ago, and he doesn't remember the price, but usually they are way too expensive. I will see if I can find something else bigger than this radiator in the future, or actually I can buy a radiator only to make this shitty test, this shitty experiment that I'm having here. It's not shitty because it's telling me something. You learn some undesired lessons at higher power. So that will be the next movie with a very big, a stupid big radiator. Hopefully, it's my desire. I really hope. But as it is right now, the setup that I'm having right now, as you can see here, I reached that 40 watts, but it's not concludent anymore, unfortunately. So at this point here, with this 20 watts that I'm having at, I should note here, 55 degrees Celsius, but it was slowly rising up. So it was rising up a little bit, very slowly it was still rising up. So I didn't leave it too much, like 5 minutes probably. I'm not sure if I leave it for 10 minutes at this, and then take the temperature. I leave it a little bit. So it's even less than 19, probably, I don't know, 17, somewhere like there, to be, with this heatsink that I'm having here, to be kind of optimal, you know, to be under 50 degrees Celsius, 48, 45 probably. That's my target. So, but even if it's this lower wattage that is functioning, it is still over the normal naked transistor power that it is handling. You know, it's over that, and this is still good. As low as it is here, it is still a good power driving for testing for something else with a very cheap component, what I'm having there, very cheap. Probably if I'm using more powerful transistors, I believe this heatsink will be way more efficient for more powerful transistors that are not so hot. They can manage the power themselves a little bit better than this one, which is barfing all the power all over the place, you know. As much as he can barf it, he is showing it all. But there are more powerful transistors that they can sink the power more efficiently than this motherfucker that I'm having here. So those will be interesting to test, but I don't have such powerful. I have something, but I wanted to have something that is more common used. I'm not sure how common use is this BD681 that I'm having here, but it's very close to some normal transistors that are used for H bridges, for motors, for other power circuits, testing boards like I'm having here, etc., etc. So this is my entire movie. Thank you very much for listening and for understanding these issues that I was going through and these errors that I was getting into them, and also resolving some of them. I believe I solved some problems, because this is telling me what I was having before was not good. This, immediately after I changed the wires, this blown up. So this is telling me that what I was having before was wrong, and the setup that I did here, that I'm having right now, is way more better. And the efficiency got very low right now, as it was before. And I can imagine, I don't see the faces of my friends, but I can imagine them, they are still making weird faces when they are seeing even this wattage, probably. They are lifting their eyebrows, and they are saying, maybe it's not good value, even that. And probably they are right, because I mentioned it before already. This amperage is the total amperage that the power supply is delivering, but I didn't get the amperage. I didn't measure it in the circuit. All right, that's it. Thank you very much for listening. Thank you very much for understanding what I did here. That's it. Bye-bye from our favorite artist electronist, Mr. Q12.